So this is the remaining schedule. Today, Abhi and myself will cover feature recognition technique, and then Alexandre, is it? Pronounce again?
Alexandre.
Alexandre. Similar, right? See, I learned French when I was in high school. Okay, Alexandre will lead on discussion, and then tomorrow evening we will have a invited lecture and and next week, and 2-3 weeks more, right? So this is the final. Because of my schedule, we will have another class in 10 instead of evening. Any question on schedule? No?
The last two classes will be on the finals week.
Probably, yes.
If it's on Monday and Wednesday, well, I don't know the schedule yet, but I might have exam for either Monday or Wednesday.
All right, then we can adjust our schedule because we are a small group. We can find other time. Please let us know through the cutoff. All right, come on in.
Good afternoon, everyone. I will be presenting chapter 9.1 and 9.2, which will touch upon feature recognition techniques. So for a brief overview of what we will cover, it will be mostly about the automatic feature recognition. And then to recall the subtasks of feature recognition include constructing data structure from the geometric model in order to search for the features. Then we can search the geometric model to match topological and geometric patterns for the recognizing of features. And then we extract those recognized features from the model and determine the feature parameters and completing the geometry model, as well as maybe combining them to get composite features. So this will be the contents that I will cover. Firstly, I will cover the framework of feature recognition, and then recognition using boundary models for 9.2. So in essence, feature recognition is based on the expected scope of what you want to get and the feature system that you want to use. So with the recognizing algorithm of your feature recognition, you can get the characteristics that you want. You can identify the characteristics and obtain the features. So the requirements for this framework depends on what you want to use your feature recognition for. Basically, you want to find and report the feature instances, but then there are other details that you need to take account for depending on your use. For example, whether it be for manufacturing or for design. So what are these detailed requirements? Firstly, it's whether you want the whole feature to be recognized or only some portions of the feature. And then that recognized feature, whether you want it to be extractable or not. And then you want to check whether the feature is valid or what kind of validity requirements you want to use for the feature. And the next one is whether you want to get the volume features or the surface features. And then how do you want to handle interactions between these features. So to decide what kind of options you want to take, you need to consider what kind of applications you want to use the feature recognition for. And these are some of the applications. First one is for during the design process, and then the next one whether the feature recognition is for your engineering analysis. And then there's also group technology coding, which I will explain in a bit, and then whether you want to use the feature recognition for your manufacturing process and planning. So the first one is design. So usually feature recognition is used on a finished part, and during the design process, usually your feature is not yet finished. But sometimes it is useful to have a feature recognition applied during the design process. And whether you want to get the whole feature or the portion, it's usually better to get the portion because, as I said before, the design process does not have a finished product yet. And then typical application of the feature recognizer program during the design process is to resize or reposition geometric elements. And for this application, it is better to have an extractable feature instead of a non-extractable feature. And since the design of the feature is not yet finished, the feature recognition must be allowed to recognize invalid models. For example, you might have disconnected faces, which is usually invalid, but you still want to recognize that. And for engineering analysis, you're only interested on the part of the feature that is important for your analysis, which is why a portion is better for your feature recognition than the whole. And then usually you want the idealization of this feature for your analysis, and hence why the extracted feature is much more preferred. Group technology coding. Group technology coding is used to analyze the shape of the part according to classification criteria. For example, whether it is a prismatic or rotational part, or whether the classification is on the dimension of the features and so on. So whether you want the whole part or a portion of the feature, depends on GT coding uses a top-down view of the part, so analyzing the part as a whole is important, which is why it's preferred for your feature recognition framework. And then GT coding is a summary of the whole part, so it's not really important whether for validity checking. And then GT coding requires both the solid model and the surface model, so both are needed for your feature recognition. And interactions between features is not really important in GT coding. And lastly, for manufacturing, this is the most important application for your feature recognition, because you want to plan your manufacturing process, and the feature recognition helps in that regard. So your finished design must be converted to features in order to create the manufacturing plan. And usually for this case, you want a subset of the whole feature part instead of a portion. And then you want this feature to be extractable so that you can choose what kind of machining process you want to take for that to create that certain feature. And various validity checking is required for manufacturing, and this depends on what kind of manufacturing process you want to use. And you can read more on this detail in chapter 11. And then you usually need both volume features and surface features, because, for example, fixture planning for your manufacturing requires the surface information, but the surface information must be viewed as a whole, as part of the whole overall solid model for your machining. And lastly, how do you want interactions between features to be handled? Well, ideally, you want the feature recognizer to be capable of generating all relevant interpretations to create the best manufacturing plan to create that certain feature that you want to make. Then next is recognition using boundary model. This is the most common starting point to create a feature recognition program. And usually boundary representations can be represented in graph structures. So the approach to for feature recognition can use the graph matching algorithms. And another approach is to use the syntactic method. So what is the graph structure? Well, usually for features, you want to, for a simplified model, you want to arrange faces, you want to represent faces as nodes, and then the face-to-face relationship as arcs between the nodes. And I can show you that in a bit. And the main advantage of graph matching is that there are well-established techniques for graph algorithms that can be adapted to recognize features. So this is an example of a graph structure. For example, we have a pocket feature with the faces 1 to 6, and it can be represented in this face adjacency graph, or FAG. And with this graph, you can see the interaction between the faces. The faces here are the nodes, and the connections or arcs between the nodes are the relationships between the faces. For example, 1 is connected to 3, 2, 5, and 4, which is represented here. But this is still a simplified model. For a better representation, you can use an entity classification. So as I said before, an arc can represent an entity type. For just now, it was the relationship between faces for the case of FAG. But maybe you want more details or more descriptive details about the entity type. And for this, you can use the attributed face agency graph, which adds more attributes to the edges of the graph to describe the connection between faces. As an example, this is the Capriano's edge classification criteria, in which the descriptive factor is the magnitude of the angle between the faces. So with the magnitude, you can describe whether it will be a convex or a concave, smooth convex or smooth concave. But consider the following case. For the above, you have a slot, an open slot for the above case, described by face 1, 2, and 3. And this is the FAG description. And you already have a method to identify the slot feature from the FAG graph, from the FAG. And this is easily recognizable. You can just select 1, 2, 3. But consider the below case. You add another slot to the overall model. And now phase 1 changed to phase 1 prime, and phase 4 is split into phase 4 prime and 4 double prime. So using the previous feature recognition algorithm to detect slots, your algorithm may detect phase 8, 9, and 10 as a slot. But you know that phase 1 prime, 2, and 3 is also a slot, but since the phase of 1 prime is different to phase 1, your feature recognition algorithm may not recognize this as a slot. So how can we make this to be recognizable? Well, this type of interaction between features is called a type 1 feature interaction. And for this, a heuristic rule approach is proposed. For example, you have a slot within a slot, described by this agency graph. So the heuristic rule is followed. First, you remove the arc of type convex. So arc of type convex involve phase 2 and 3 and phase 5 and 6, which is this arc here, 2 and 3, and 5 and 6. And then you split them and you obtain this B. And then the second rule is to join the split faces. So you join the split faces, 6, 7, and 1 and 2, join together, and then you have a way to recognize 2 slots for this particular model. But this may still may not be sufficient, because some faces may be shared by some faces might be shared by how to say more than 2 features. For example, phase 2 for this case, phase 2 is shared by 5 and 6 and 3, 4, and 1. And this is called a type 2 feature interaction. And for this method, a different way to determine which faces are split is used. And the first rule here is determine split faces and call this set A. So we find phase 3 and 4. So this is the original one. So we find phase 3 and 4 to be set A. Then set the faces incident to A at the concave edge as set B, which is phase 2. Phase 2 is concave edge to set A. And then you find the faces that causes the split. And for this case, it will be phase 5 and 6. And then we call this set C. So the shared phase is the union between set A and set C. And this is how we can determine which faces are split faces and which face is a shared face. And a different method for feature recognition is a syntactic recognition. So this method tries to use the characteristic of the boundary graphs to be more expressive and to be faster. So this process is based on pattern recognition. So what is a syntactic pattern recognition? There's basically 3 steps. First, you extract contours of the shapes from your image, and these contours will give you the lines or arc segments. And then you will match the patterns of these extracted contours to predefined patterns that you already have. And once you've matched these patterns, you can then perform your necessary action. So as an example, I will show you this video. So this is just a different way of using pattern recognition. So the image may be dynamic, but then the process is to detect the contours, or in this case, the edges of the objects. Then you classify them to what the machine learning program have learned. So this is an example of how we can use this approach of pattern recognition to feature recognition for feature recognition. Say you have this 2D representation of a whole shape. Then you have 8 primitives representing various orientations from A to H. So to describe the whole, the orientations will be arranged like this sequentially, and you can represent this symbolically using C, D, and then E to the power of n, where n here is the number of repetitions that you need to take. For this case, n is 2. So you can see that first you start with the C orientation, then next one is the D orientation, then the E orientation twice, and then the C orientation, and so on until you get the 2D whole shape. And you can use this same approach for your 3D representation. Here is the classification for whole classifications. And first we have the HSS, which is the whole starting surface, and then we have the HES, which is the whole element surface. And there's 3 types. HES 1 is for cylindrical, 2 is for conical, and 3 is for circular planar area with concentric circular holes. And then you have HBS, which is the whole bottom surface. And then you also have three types. The first one is just the circular planar. Then you have the cone, and then you have another hole, the HBS3. So these are the classifications. Then for different hole types, you can then use these for your feature recognition. For example, a straight hole will be HSS, HES1, and HBS1. Maybe there's a countersink example. So this can be described as HSS. So first you have the surface, then HES2, using HES2, the conical hole, and then you have HES1, the cylindrical hole, and then you have HBS2, which is another conical hole to describe this particular countersink. And with this approach, you can then describe various other holes for your feature recognition algorithm. We also can use graph grammar, which is the formal descriptions of a class of graphs. So graph grammars is used by feature recognition similar to the graph-based method, but in this case you have production or rules that contains a graph that needs to be matched, and a second graph that shows how the part graph is changed when there's a match between the features. So the feature can be identified in steps. First, is by defining the production that recognize the basic shapes from the feature and labeling them on the part graph. So first you, for example, detect the faces, and then you compare this to another graph that recognize the labeled feature description. So as an example, the production here is this one on the left, PF1, PF1, and CF6. And then you also have a subgraph that defines a true hole for these spaces. And using the same rule, once you've compared these two, you can then apply it to, for example, this model, and the model that defines the true hole will be then PF1, PF3, and CF6. So PF1 will be the planar surface 1, and then CF6 will be the internal cylindrical surface 6, and so on. And a different approach is a rule-based algorithm. So instead of using graphs, we use rules, which is written like a computer code that is associated to certain feature definitions for recognition. As an example, this is a rule to describe holes, and we have 4 rules here. It starts with the hole begins with an entrance face, and subsequent faces of the hole shares a common axis, and faces of the hole are adjacent, and then the hole terminates with a valid hole bottom. Basic descriptions of what a hole should look like. And this is just the pseudo rule, and for a code description of the hole, you can see it in this case. So there are the definitions. And that concludes my presentation. Thank you. Any questions?
I wasn't sure why, how you use feature recognition and group technology coding. Can you go back to that slide?
So this is just what kind of feature recognition framework you want to use for group technology coding. And so since group technology coding is just the classification or classification criteria of the features, these are just the frameworks or the basis of what kind of the feature recognition that you want to use for this case. So GT coding has a summary of the parts that you want. For example, its overall dimension, its function, its basic function, and so on. So with this approach, since they already have a summary, you just require the whole part for the feature recognition, and then this validity checking is not vital already, since the classification is already well defined, and the classification also already includes both volume and surface features. But yeah, for the feature recognition, so for the feature recognition, you need to use both. Then this is not really a major issue, since GT coding is select to portions of that part. I mean, yeah.
Okay.
Okay, thank you.
Right. About the group technology. Group technology in general is classification. Say you have a pieces of Lego blocks, and then you try to grouping into similarity. Right? So while you are classifying them, you need to recognize features of each part. Right? And comparing or grouping, gathering the parts with similar or same features can be one classification. All right. Then second part. So feature recognition still. We are working on chapter 9. So the textbook is coming toward the end of the semester. I will cover section 3 to 6, decomposition, CSG, 2D drawing, and comparison. And volume decomposition, there is 3 subtitles saying volume decomposition alternating sum, and delta volume, and also the multiple feature models. And alternating sum, and there is also 2 different ones, but almost the same. But this one is improving. They found some problem inside, small problem, error, or not error, disadvantages, so they improved that one to it. Partitioning with partitioning. So this is coming from 82, long time ago, right? Long time. Well, when I was a student in Michigan University, Tony Wu was one of my, not supervisor, he was in my committee member, PhD committee member. So, this is a new slide I include in this morning. So, I will upload a new version to the talk. Anyway, here, same idea, but some small difference is convex hull difference. Convex hull. What is convex hull? Minimum
volume that
encompasses
all the whole.
Right. All right. And one more characteristic is convex. It should be convex. Not concave, convex hull. Right? So this one is convex hull, right? Convex hull of this part, right? And this is a difference. Difference means minus. So this one and this one combines into this one, right? Yes? Right. So in this way, and then they start again finding out convexor of this new part and this one. And then difference, use convexor difference. Again, this is a new part, convexor. Difference, find out this one. Until this is null. Right? This is a volume decomposition. Convexor volume decomposition. So in writing, we should see that convexor difference. It is a difference of convexor and part. Right? And this convexor difference is a deficiency of the part to make part it in a convex volume. Right? So the part can be decomposed into P and C, convexor and convexor difference. And repetition until null. Already explained this one. So this is the convexor decomposition idea. So similar picture, but notation is different, right? Convexor difference. Convexor difference. In this way, they arrive at decomposition, convex or decomposition. So this is a new one. This is a Yong-se Kim. He is a professor in Soonhung Han University in Korea. So when he was studying in the United States, he improved that previous work. You see that after 10 years, right? 10 years. So he solved the problem of convergence. Well, once you, this one or previous one, you arrive at the decomposition tree of part P, then you can generate from here form features. And then the form feature can be converted into or classified into domain-specific features. Engineering features is a domain-specific. I already say this is a meaning. Meaning means application or some use, right? That depending on the usage. So it is not mathematics. So it is not clear. Right? Mathematics is clear, but domain-specific features is not clear. Anyway, form feature is more mathematics. So it is coming from, this one is also mathematics, you can say, right? Volume decomposition is mathematics. Form feature still looks like a mathematics, and then you can convert it. So form feature is a shape, and then you can is domain independent, right? Domain independent. But final goal is domain dependent features. All right. So you already see this one, very similar, and the difference between them, they are good, both of them good, general, and is very decomposition is unique. It's something like a mathematics. But problem is that includes positive and negative features. So finding differences. And manufacturing, you need one more steps to modify or to enhance them for the usage. So you need one more step. And there is another method called delta volume decomposition. The delta volume means difference between stock. Stock is the raw material, box of steel. Then you're trying to machining to arrive at final result, right? The starting point of machining. We call this as stock. And stock and the final part, the difference we call delta volume. That should be removed by some machining operation, right? So that stock minus delta volume, then you arrive at finished part. And delta volume is remaining as pieces of metals, right? but because of milling machine gives you small pieces, right? No, mathematically different. This volume is decomposed into units that correspond to machining operation. Right? This volume means delta volume. So delta volume decomposition is very similar but more smaller units. Right? So general delta volume is equal to meet the complete and rich, and the material removed and also material removed. So this is they have classified delta volume types. So rotational, it is related to the machining method, right? And transitional, also milling machines. But there is a throw hole and also blind holes. So very simple classification of delta volumes. Once again, it is machining method dependent, right? Machining method. You remove material, delta volume material from the stock. Okay, another section is multiple feature models. So they report all possible sets of features. And then you can have different ways of viewing, so alternative ways of, so from full set of features you can planning in this way or in this way. So alternative ways of machining. So it is good for machining planning. CAPP, process planning. Right? Process planning is machining planning. There's two ways, cell decomposition and there is volume reasoning. So cell decomposition. So once again, delta volume is appearing. Subdivide delta volume, divide delta volume into subvolumes, into cells, elementary cells. Right? And then generating partitioning, dividing. And cell should be convex, minimal, and unique. You'll see that details later. So something like this simple cells of this small pieces. So delta volume can be divided into, how can you partitioning? Here is, they use a help space. Help space is a long, big, straight spaces. One of the partitioning way, right? Depending on the region or length. And this is another one, geometry reasoning by volumes. There is a form feature. Once again, this is domain independent, something like mathematics. And in ISO standard, there is a separate standard book which defines all the form features for the machining. Right? It is a formalization of feature search on the basis of algebraic and geometric reasoning, so that manufacturability features is important for them. So manufacturability means also depending on the facility itself, machine itself, machining machine. So it is a little bit complicated model here. Anyway, there is a S in all the features. Feature extracted by research person. They are based on NIST. NIST is a National Institute of Science and Standard and Technology of the United States. CSG3, they start from CS3 and rearrange that tree to arrive at feature recognitions. So node of CS3 has features, and relocate, rearrange, and grouping into subtrees. There is another way of recognition of features. Okay. So there are the papers also old enough. Principal axis and tree reconstruction. So they start from CSG tree. CSG is reconstructed and transformation. And then another one is machining region extraction based on CSG and octree. And they show some pictures on objects and then CSG tree. This is already we studied in CSG, right? So how can you rearrange this one to arrive at feature recognition? So they explain the steps of recognizing based on CSG tree. I'll not explain all of them. And here is a code tree. Code tree means 4 children, right? 4 means code, right? And then this one is cell decomposition method. Right? Cell decomposition of any material. This is a 2-dimensional method. 3-dimensional, you need to have an oak tree. Right? Box is divided into 8 parts. And CSG tree again, binary tree here. Right. And then 2D drawings, recognition is old drawings. Right? You have lots of old drawings, paper drawings, and also digital drawings too. AutoCAD in the 80s. This book is written old, 10 years, more than 10 years ago, right? So at that time, or still, there is a lot of paper drawings and also 2D CAD drawings, AutoCAD. Right? And then I want to use 3D parametric feature-based CATIA GMS nowadays. I don't want to play with the 2D anymore. Then you need to convert them into 3D feature models. Right? So that you need to recognize this drawing into, then you can convert, right? Human eyes. Humans can recognize 2D drawings. And then he can model manually 3D. But here, they want to make it as an automatic conversion. How can you do that? So transition, manufacturing. So there is a papers, there are more, anyway, fleshing out. Fleshing out means one line can be broader, face can be box. So wireframe can be recognized into 2D vertex, edges, and 3D vertex and edges, and 3D face, and so fleshing. So more dimensions. And this is one example that here is the given 2D drawings, right? Front view, side view, and top view. Then you recognize this edge. This edge, it should be here. So by using that kind of recognition, you may arrive at 3-dimensional shape. But once again, human can understand. If you have a chance to learn how to draw these drawings, right, in your school, then you can, by using your talent, but machine or computer need to have more algorithms to convert it into this alphabet. This is a more complex drawing, right? Complex drawing, 2-dimensional assembly drawing. How can you recognize this one? You need more experience, right? Okay, then go on to feature recognition technique comparisons. We already see by previous presentation rule-based feature recognition and graph-based recognition. I explained about volume decomposition based method, and then they have a different advantage and disadvantages. So rule-based. It is good, but it needs a heavy computing. Right? So geometric reasoning should be burdened to speed up performance problem. And also rule cannot be well generalized. And you need to have an exhaustive search in rule base. So you need to have a matching rules, find out matching rules. If you have a rules of say thousands or tens of thousands rule base, you need to have a search so that performance can be a problem. And graph-based feature recognition. It is good for locating that feature many times because it looks like a pattern recognition of graph. For feature interaction, it is not good, so it can be unstable. Feature interaction means two features are meeting together, overlapping together. Graph algorithm is depending on graph topology. There can be a difficulty. So also it is a speed problem too. Volume decomposition. There are several candidate models, and it is good for the application. And it is also good for, it is a general method. You can apply to many different problems. But still, at that time of book, it is a new technology, so that only simple models are solved at that time. Now, it is also a new slide. I will upload that. More after that book is written, there is a collection of ideas on hint-based recognition. Is one group, and then now this is not well theoretical one. This is something like a commercial, but anyway, this is another idea behind that. And Abi already showed us that image recognition. It is a little bit different from our CAD model feature recognition. But anyway, they also use saying feature recognition from images. Video, we showed, right? But we need this one very well, right? Robot vision or fingerprint, they should find out features. The features are a little bit different from our concept, but still it is features. All right? Yes, all right.
Yes, sir. Going from domain independent to domain dependent. So we try to find, there are different possible ways.
Right.
So is it similar to topology optimization?
I don't see any relationship there. It is similar to using mathematics for your design. So mathematics is already there. But how can you use them for your real life world is depending on the situation, depending on the problem. So that form feature is already mathematical library there in ISO standard. But for your problem of real world, you select some of them and combine them into solve that your problem. That is the way we can relate to them. From theory or mathematics to the real engineering world. Selection, combination, and application. Any other questions? No? Then we go discussion.
So, hello everyone. Today I'll be leading the discussion session. The topics I've prepared are these ones. So, first CAD collaboration, and then reinventing the CAD Design Workflow. We'll see a bunch of videos. So first off, CAD collaboration. So yet we have not talked about how people actually work, or multiple people work on the same project, how it actually works and how it's done. So I have an example here of some state-of-the-art technology for this. Fix this.
the upper central base plate, editing the lightening reliefs. Let's see what happens when Don joins us. We note from simple visual cues that Don has entered the document. He has uploaded a standard battery pack that he is considering. It happens to be in SolidWorks format, and while Don is working on that problem, we can move forward with the editing of the lightening reliefs. Each of us is working simultaneously with the same document. Let's switch over now to the main assembly tab, where we see that Don has inserted the new battery pack. Each of us can work and see changes in real time anywhere in the document. We can work on the same assembly, the same part, and even the same sketch. Now, what happens if we don't want to work simultaneously with someone? What if instead we wanted to work independently to evaluate a design concept or potential change, and then merge some or all of those ideas back into the main design? From the version manager, you can create branches from any named state, forking the design at that point and enabling parallel independent development efforts. Here we are creating two branches, one arbitrarily for assembly changes and the other for geometry development. Remember, the benefit is the ability for groups to work on the same design independently and to evaluate competing or what-if scenarios. Let's work now, logged in as Don, and make some changes. On the geometry branch, Don would like to add some fillets to the horizontal arm plate. We can imagine that he and others have now made multiple edits and that we should now mark this new state as a version. Switching now to the assembly branch, we see Don adding a 12 kV 28 amp brushless motor to the arm and motor subassembly. We are not going to version these changes quite yet, as we may not be done. Returning now to our original user and his work on the main branch, we can see that none of these changes just made are reflected here yet. As a result of a design review, we may now wish to incorporate the changes from one or more branches. To do this, we go to the version manager and invoke the merge capability. Merging takes as input any other branch or named state and intelligently incorporates the differences between the workspace on the current branch and that other workspace or named state. Here, we are merging from the geometric edits state into the main branch. One more time, here we are merging from the assembly branch workspace into the main branch. As a result of these operations, we see that the geometric changes Don made have now been incorporated into our design. Here are the fillets he added. And the brushless motors that were added in the other branch are now also present in our top-level assembly.
So that was an example in would look like an industry setup, like for building drones in this case. But this kind of technology also exists in other domains. For instance, purely design. Okay. Yep. So what do you think of this new take of this online collaboration tool? The pros and cons, etc. Maybe the challenges.
It obviously saves time,
Yes.
but when you showed the merging process, I think that still requires maybe a team meeting or some sort of agreement between the
Yeah,
teams.
good communication.
Yeah.
Yeah, that's true. Like you can easily mess up. For example, if one people is working on a sketch and another people like deletes the surface people was sketching on, that could be problematic. So of course you need to have good collaboration, a good communication.
One obvious con may be that dependence on internet and internet speed, right? I mean, it uses online connection,
Yeah.
right? So
I mean, we have like live online gaming, so and that uses way more bandwidth than this. So I guess this could work quite easily.
The bandwidth is different from the processing, right? In the case of CAD or rendering, we use a lot of GPU power. So doesn't that from make this a online?
You know what you
One potential issue would be the security of the design. Since it is online, so it would be some.
yeah, that's the problem with online collaboration. But it has many benefits, so I guess it overcomes the difference. Yes.
For collaboration, they need to run, they need to use the same system.
The same like CAD system, CAD software. Like, you mean, for instance, someone was working on SolidWorks and someone on CAD. Yeah, like for this, for instance, like the people only worked on Onshape. I guess it would be quite difficult to have collaboration between different softwares. Yes.
but we saw one guy upload a SolidWorks part.
Yeah, but the part was in SolidWorks format, but still it was open in Onshape. So here are some pros and cons found. So one another big advantage of this is having an history of change. So for instance, if you want to discuss design, maybe you want to go back, it's easy. Because as you saw the tree with all the changes. And so, yeah, you need proper communication, otherwise it could get really messy. Next, I want to move on to another topic, reinventing the CAD Design Workflow. So, for now, we used to, like traditional process when we design on CAD is select a plane, draw a sketch on it, extrude that sketch, and it can be pretty slow, pretty tedious. And so I have a quick video that answers to that.
CAD represents a fundamentally better way to design in 3D. If you're new to CAD software, it's a lot easier to learn. And if you're an existing CAD user, it's so much faster and more flexible than traditional 3D CAD systems. CAD's advantage starts with letting you design in 3D from the beginning. You can skip the traditional steps of creating a plane, creating a sketch on that plane, and then creating a feature or extrude from that sketch. CAD has a range of predefined shapes which you can simply drag and drop out. You can then push and pull them to make precise changes in seconds. These shapes are features in disguise. They still have cross-sections and feature types which can be edited anytime. You can also save custom shapes and make your own custom catalogs with a simple drag and drop. This method is faster, easier to understand, and you get to skip the boring steps. These shapes and catalogs also have more advanced functionality built in, which we'll cover later in the video. You may have noticed we are designing multiple parts with one file. IronCAD has a unified design environment, so you can design as many parts as you like in the same file. This, of course, makes file management a lot easier compared to the traditional idea of having many individual files, but the advantages don't stop there. You're designing within the context of the assembly, which is a more natural way of thinking about your design. You can snap to existing parts, and everything fits perfectly first time. You can also largely skip the mating and constraining process with traditional CAD software. Traditionally, we would make every part individually, and at the end, bring them into an assembly and mate and constrain them all together. In IronCAD, they're already in the right place, so there's no need to do this. Then if you have moving parts, you can simply apply the movement constraints to those parts. All other constraints can be skipped. Anyone who's constrained a large assembly in a traditional CAD system before will know how much time IronCAD saves here. Traditional software is history dependent, so features are dependent on other items above or below them in the history tree. This makes it difficult to make late design changes, and also results in these other systems often having history tree crashes, which you may be familiar with. IronCAD features are independent, so they can be moved up and down the history tree easily. This makes design changes easy because you don't have to worry about the design intent from earlier in the model. IronCAD lets you choose when and where you'd like to use design intent. This provides better control over your design and means changes that may have taken hours before can be done in minutes. This feature independency also makes it easier to reuse features and models. You can drop them into a catalogue and then drag them into other parts and assemblies, where they can be customized to suit the new model as if they were made there in the first place.
So if you've already worked on somewhat big project on CAD or on other software, you know the pain when you have to redesign, go back far in the tree and redesign some parts. You often have those crashes. It takes a really long time, and this really is like crazy because it overcomes many of the problems you often come across when designing in CAD software. So what could be like the most obvious pros and also some cons?
When you are working on some already made part, you are just updating it. The history helps you understand how it was made.
Sorry? Oh yeah.
This history independent, right?
Yes. Like you say, the parts that you drag and drop and modify are still are features that have still characteristics to it. So yeah, you lose that history, but then.
And also it's non-history, but still it is parametric and variational.
Yes. So that's what's important. What's crazy. Yes.
Is it using the object-oriented approach for the data structure and
I don't know.
You can still make custom shapes, right?
Yes. Like you have a lot of pre-made catalogs. Like on the website, you can actually download a lot of catalogs depending on the domain you're working in. For instance, you have catalogs for architecture, or nature catalog with some trees in it, I guess. And so you can import them quite easily and drag and drop. And you can also create your own catalogs that are basically like preset features and use them.
One of the pros can be that you don't need to learn all the other features as well. If you're going to modify one specific, you don't need to know about the sketches or the previous features. You can just learn about that and update it.
Yeah. There was another example in the video where the people were designing a cart, a shopping cart, and there was a wheel feature. They removed it very easily, and then took another wheel and just grabbed it and popped it on the cart. So very easy modification. So here are some pros and cons I found. So obviously it's because it's drag and drop and you don't have to go to 2D to 3D. It's much more natural and quick to work with. And like the big step of having to assemble the parts that you've made is completely skipped because you build directly in the assembly. Everything is in one file. But you may also need a lot of these catalogs, these parts. So it may need some work before you actually start modeling, just to make up these features.
How are the constraints defined in this program? Like, do you have to define it yourself, or is it automatically generated when you combine two features?
There was a small example in the video.
Yes, it says that the features are independent.
Stop there.
Like when the
This, of course, makes file management a lot easier compared to the traditional idea of having many individual files. But the advantages don't stop there.
you see when they have that plane constraint, right when you
It's snapped to existing parts, and everything fits perfectly first time.
see.
And so, for example, if you change the black feature,
Yeah, it would
Such that
automatically adapt. Yes.
but if you change it such that the previous constraint definition does not apply anymore,
Oh,
for example,
yeah.
the shape is totally different.
So yeah, if you have plane constraints and then you give it a curve, so
Yeah.
it's not plane. Yeah, I guess it's one of the crash that you would usually have in the older systems, but yeah, it still happens. But I guess, but way less than before.
It can be a good for say special company, say bicycle manufacturer.
Yeah,
You can have a set of special features.
yeah, it's great when you want to
Primitives,
custom.
complex primitives, and you can combine them to produce a new bicycle manual.
If I can find the card example.
Generative design.
You're not good for surface modeling.
Oh,
Surface.
Surface modeling. Because with the surface you have to have some control points and I did not see anything with respect to surface.
I guess it's just I don't know what.
I think the surfaces are inside the motor features. There are a lot of features, and when you select one from catalog, surface relations are defined within that one feature. So, but the problem is that for all the features, we need to separately define the surface relation. That is one of the cons of the
Has this software been commercialized? Is it
It's really new. It's just being commercialized right now. They're putting a lot of effort into marketing because of this.
Belgium?
I don't know. About optimization, this is a quick demonstration how to quickly have a modular
It contains both parts and assemblies.
modular
Snap into their exact location.
object.
Be swapped in and out in seconds.
Customized.
This functionality can be used throughout RineCAD products. So you can make a catalog in RineCAD
CSG.
for someone using the free
Image is very
Decomposition or iPad app. They can customize
Why
it,
work
make
when
annotations,
creating
and send it back
optimal
to you.
design? For example, using Professor's example, if you're a bicycle company and you want to design a new aerodynamic frame, you still have to start from scratch, right? You still have to start from the sketches.
Yeah, you create that.
Sketches are not usually required, like you
Oh,
sketch
sketch.
for making a 3D, but if you already have the 3D.
But you want to create new aerodynamic design, like not defined previously.
You have a handle already, you can modify handle. But using handle primitive from the menu, come in down and then modify for the fluid dynamics.
Well, but maybe more complex, like the frames, like maybe different shapes or different.
Maybe you can modify the primitive shape, right?
Yeah.
Yeah.
And
Make it curved or something.
And you are a totally different shape, then you need to start from scratch.
You may request the company, okay, add this feature. That's where we get our.
But it is their promotional degree.
Yes. But it has quite impressive technology. So,
Yeah.
All the promotional videos look very.
Any other question? Okay.
Okay, good. See you tomorrow evening, 7 o'clock.